between us and the upper row. So we will have one more talk, then there will be an upper row, and we can continue the discussion there. Now we have David Kolb from KNIME. He's showing you how to use deep learning in an interactive workflow system or in a process. You say, well, he says something about KNIME in a second. Okay, now let's start.
So thank you for the introduction. So the topic of my talk is deep learning with KNIME and deep learning for J, which you heard about in the last talk. So I'm going to tell you how we integrated this in our software. So for the agenda, first I'd like to talk a bit about who we are and what we are doing for all of you who don't know KNIME. Then I want to give a quick introduction of our software, of the KNIME Analytics platform. Then I want to talk about how the deep learning for J integration works in our software, and then I'd like to show some examples and some applications how you can use deep learning in our software. So let's start with what and who is KNIME. So we are founded in 2008. We have offices in Zurich, Constance, Berlin, and San Francisco. Then currently we have 120 employees, and we are the maintainer of the open source KNIME Analytics platform, which is a powerful data analysis and pre-processing tool. The one nice thing about it is it has a visual front end, so you can create your data pipeline without having to write a single line of code. Of course you can if you want, but you don't have to. Then our motto is that we are open for innovation. This means that we are open to, for example, all sorts of different data. So for example, images, specific data types from biology and many more. Then we are also open for other tools. So like for example, the library Deep Learning for J or R and Python. So there are integrations for these languages, so you can run Python code or R code in our platform. And then the whole thing is open source. So you can use it for free and look at the source code. So here you can see a screenshot of our software and of the visual front end here in the middle. So in KNIME, you create your data pipeline as workflows, which consist of nodes, and these nodes perform a specific task on data, and you would connect those nodes to specify the flow of data. Generally, the data flows from the left to the right, beginning with some node which reads in data. And now the nice thing here is that you can easily create sophisticated data pipelines with this visual front end, and you always see what's going on because this visual view is a representation of your workflow and what you're actually doing, so you can see what you're doing by looking at the nodes. And here you can see a more detailed description how a node actually works. So a node has some parts. So we have some inputs. So we can have 0 or more inputs, which are shown as these black triangles. These represent data tables. Then we have the nodes itself. In this case, it's a partitioning node, which gets an input table and partition it in 2 data sets using a user-defined configuration. Then we have the output parts. And here on the bottom, we have a status display, which shows the status of the node. So we have 4 different statuses. So if it's red, it's not configured, and it's waiting for more user inputs to be executed. And if it's yellow, it's idle and it's ready to be executed. When it's green, it's executed, and you can access the data at the output parts. And if there's this red X, it means that there was an error during execution. So, and as I told you, you would combine these nodes to create a workflow and specify what you want to do. So currently we have over 1,000 nodes which do different things. So for example, for data access, we have nodes which connect to databases, or you can read simple text files, or for example connect to the Twitter API. Then we can also connect to big data frameworks like Hive or Spark or Hadoop. Then we have some nodes for transformation, so doing some pre-processing of your data tables or doing some data cleaning. Then we have nodes for data mining and analysis. So for example, we can train models to create predictions or calculate some statistics. Then we have nodes which visualize the data, so for example standard scatter plots or line plots, or more sophisticated stuff, for example like a tag cloud if you're working with words. And then for deployment, you can write your data back to a database, or write it as text files, or do something else, or create reports. So next, I'd like to show you a quick example how this all works and how the UI of our platform works. So here you can again see our platform. So it consists of some parts. So here in the top left we have the Explorer, which manages your workflows. So we have local workflows saved on your PC, or you can connect to a server and share workflows with other people. Then we have the node repository, which is divided in some categories, where you can choose all your nodes from, and you would just select the node which you want and drag it into the middle part, which is the workflow editor, where you would create your data pipeline. Then here on the bottom we have the console, which shows outputs of the node, and here on the right we have the node description. So if you click on the nodes, you would get detailed description what the node is doing here on the right, and see some information about the configuration options it has. So here you can see the workflow, or a basic KNIME workflow, and just want to show you how this basically works. So for example, you would here read in some data using a file reader node. This would point to a text file on your PC, and would read in. This would look like this. So here in this example, we read in the iris dataset, which I think most of you know, which consists of some numerical features and one class value. Then, for example, we may want to visualize it. We can use a color manager, so we can assign a color to each of these rows corresponding to the class, which looks like this. And then we can maybe connect it to a scatter plot and open the view and plot the data in a normal scatter plot. Then we may want to do some analysis. So we want to train a classifier to predict the class value of the data instances. So therefore we first would use a partitioning node to split the data in a test and train set. Then we can, here you can see the configuration, and here you can configure how you want to do your split. Then we can use a classifier, or in this case a decision tree learner, which learns a decision tree model. And in the configuration you can configure all the model specific parameters. And after the node finished learning, you can actually look at the tree it creates and at the splits. And after training, you can use a predictor node, which corresponds to your learner node, which creates predictions for your data set, and then use a scorer, which creates a confusion matrix, so you can evaluate how well your model is doing. So this was it for the general KNIME introduction. Now I want to introduce how the deep learning actually works in KNIME. So we have this deep learning integration since the version 3.2, which is was like 3 or 2 months ago. Then it was integrated with the library deep learning for J. The integration consists of a set of new nodes in order to perform deep learning in KNIME. And this allows you to use deep learning networks and methods in our software. So what is deep learning for J? This was also explained in the previous talk. So it's an open source library for Java. It supports state-of-the-art deep networks and architectures. Then we have GPU support, so you can actually run your workflows on your graphics card. Then, of course, the very nice thing is that it runs on Spark. And we also have integration for some neural language processing. So specifically, you can create, or it has implementation of, or to learn word vector models, which was also previously mentioned in the talk. So now how does this work in the KNIME integration? So with this integration, you can now visually create networks using our node system. Then of course, as I mentioned, you can learn either on CPU or GPU. This allows you to create predictions for complicated data sets. And there's also a node which allows you to create these neural word embeddings. So now the nice thing about deep learning in KNIME is that you can deploy your whole deep learning pipeline in a single platform. So you can take advantage of existing KNIME functionality. So for example, if you're dealing with images, we have integration for image processing, or if you're dealing with text processing. So you can do your whole data pre-processing so the pre-processing which is needed before you feed the data to your network in our platform. So as I told you, the integration consists of some nodes. So the first part is to create a network architecture. This is done by layer nodes. So at first we have a node called the model initializer, which is used to start the architecture. Then we have nodes for convolutional networks, so a convolutional layer, a pooling layer, then one special thing with the local response normalization, which is used in some more sophisticated architectures. And then we have a dense layer, which you also can use to create multi-layer perceptrons. And then we also have some layers which are trained unsupervised. So for example, the autoencoder or restricted Boltzmann machine. So with these nodes, we can now create some architectures. So for example, multi-layer perceptron, which would look like this. We also have some pre-configured nodes. So these are called meta nodes, which are just wrappers and contain other nodes. So for example, this would be just wrapped in this meta node, and we have deep one and a simple version. Then we can create a convolutional network, which would look like this. And we also have some pre-configured nodes, so like NENet or AlexNet. Then, of course, the same for deeply leaf network. This would consist of some restricted Boltzmann machines, and again, pre-configured node, and the same for the autoencoder. Then next we need to actually train our network. So we have some learner and predictor nodes. So the learner nodes are divided into three use cases. So we have a node for regression, one for classification, and one which performs unsupervised pre-training of your network. And this depends, so the node you choose depends on the created architecture. And then for all these nodes, we have one predictor node which creates output of the network and is able to, in the case of classification, to predict class value. Then we have model input and output nodes. So it may be very beneficial to, after you train the network, to write it to disk and to share it with other people. So we have a node for that. So this is called the deep learning logic model writer, and corresponding to that the reader, which just points to a file, and you can read a pre-trained model and use it for predictions. And then regarding the neural language processing stuff, we have a node which learns word vectors. Corresponding to that, we have a vocabulary extractor, which would take a learned word vector model as input and extract the actual word vectors and the corresponding words from it. And then we have a word vector apply model, which takes sentences and the model as input and is able to convert sentences into vectors using a previously learned word vector model. So now I'd like to show a basic workflow, how this would look like. So here we have 4 parts. So at first you need to start your architecture, then you would create your network, in this case a 2-layer perceptron. Then you would learn on data. So here in this meta node we read in some tables and configure a classification learner to perform classification. And then we would use a predictor node and also some test data to create predictions. So now maybe you notice these square connections. So they are not like normal triangles which correspond to tables, but they are specific model parts. So these, in this case, this part contains deep learning model. So which layers are contained in the model, which looks like this. So here you have some information about the network type, which layer it contains, or the feature columns it was trained on, or the labels. Then you can configure each layer separately, like you've seen before in the code example, which was shown by my speaker before me. And here you can open the configuration of this node, and then here you can specify things like the width of the network, so the number of output units, or if you want to choose a specific activation function for each layer, you would do that here. Then we have a big configuration panel for the learner. So here can you specify our learning parameters, so for example the optimization algorithm or the updater to use. Then of course the size of the mini batches or the number of epochs which it should train on. And there you would also choose your feature columns from your input table, which are used for learning, or here in this case for classification also the label column. So this was it for a basic introduction of how the deep learning works in general. So now I'd like to show you some applications, how some things can be realized in our platform. So I'd like to begin with regression. So here we want to do housing value prediction. So we want to predict the housing value of homes in the Boston suburbs. Now to do that, we want to do regression using neural network. The data set we are using is the Boston housing data set, which has 500 instances. We have 13 numerical instances and 1 numerical target value, so we want to do regression. Here you can see how the features look like. So for example, we have some features showing the crime rate or pupil-teacher ratio, and here in the bottom we have our target value, which is the value of the homes in thousands of dollars. Here you can see the overview workflow, how this would work in KNIME, and I'd like to go through it step by step. So first you would create your architecture. For the simple example, because we only have 500 instances, we only use a multi-layer percentron. Then after you created your network, you need to load your data, which looks like this. So you would need use a file reader node to read in your text file, and then you can do some normalization using a normalizer node. In this case, we would use Z-score normalization. Then after that, of course, we partition it into a training and a test set. Use the learner node, which fits the data. And here for the regression learner node, we can actually choose several columns as targets, so we are not limited to only one target column, so we can perform multiple regression. Then after learning is finished, we again use the predictor node, which creates a list of output activations. In this case, it's only because we only have one target value, we only have one output value, which looks like this. So here you can see a table of the ground truth target value and the predictor value. And now in order to evaluate how well we are doing, we can use a numeric scorer node, which calculates measures like the mean squared error or the mean absolute error. So we can evaluate how well we are doing. The next example I'd like to show is celebrity face recognition. This is using classification. So here the problem is that we want to recognize the faces of celebrities in web images. How do we do that? We perform image classification using state-of-the-art deep convolutional network. So in this case, we use AlexNet, which was mentioned before. The data set we're using is the data set of celebrity faces on the web from Microsoft. It's a very large image data set consisting of over 200,000 images. And here you can see some examples of that. It contains more than images from 1,500 different people, and additionally we have bounding boxes where the faces actually are. So for the example, we use a subset of this image set. So first we crop the faces from the images, which looks like this. Then we select the 20 most frequent classes, which results in a set of 27,000 images. So here again you can see the overall workflow, how this would work. For this we use AlexNet, which looks like this, which is a very big convolutional network with many layers, and we also, additionally to the traditional convolution layer and pooling layer, we have some response normalization layer, which do some more advanced processing stuff. And this network is able to perform very well on big data sets and is able to deal with large images and with overall complicated data set. So then after we created our architecture, we of course again need to read in our data, which happens here. So here we use a list files node. This points to a directory and just lists all the URLs of all files contained in that directory. In that directory we placed our images. Then we use a small code snippet to extract the class value, because the class value is encoded in the file name, to extract the class value from these paths. And then we can use an image reader, which reads all images in our platform. This looks like this. So here we have our URL, then we extract the class value, and here the images of our faces. Next, we want to do some pre-processing because that's important, otherwise the network won't work. So first, for complexity reasons, we first use a projector node which projects for the 3 color channels to 1 channel. Then we need, every image needs to have the same size for our convolutional network, so we use an image resizer which resizes all images to 100 by 100 pixels. And then we use an image converter and an image normalizer nodes to normalize the image values. Then after that, the images look like this, so they have the same size. Of course, some are more pixelated because of the upsampling, which was done with the image resizer node. Then after our preprocessing, we join our preprocessed images again with the label because this information was lost during this process. And again, we split into test and train set. Then on the train set, we do some shuffling, which is important for our stochastic gradient descent. Then we use a feed-forward classification learner. And during learning, you can actually look a bit what's happening. So it has a view which shows on what epochs it is training and the current loss of the learner node. Then after learning is finished, we again use the predictor node to create predictions for our test set, which looks like this. So here we have our test images. Then in the middle we have a vector of the raw output activations. These are softmax activations, so we can choose the class with the highest probability, and this is here in this column for the prediction of the network. Then again we can use a scorer node, and see how well we're doing. So in this case we had an accuracy of 86%. So now, because this network is very computationally intensive, so you may not want to train it on your laptop, so you would use a bigger machine, train it, and save it on your disk, and share it with other people so they can use it for predictions. This is the problem described here. Therefore, for this we would use the model I/O nodes, which I showed you previously. This would look like this. So after we train our network, we just use this node, specify a path, and it would write the model to your disk. And correspondingly, for reading, you would do the same. Just use the reader node, specify a path, and after reading, it's perfectly fine for it.
So you just for scoring.
Sorry?
This will be used for scoring on another machine.
Yeah, okay. For example.
Yeah. Okay.
Or you could also read in this model and connect further further learner node and train it on other training data.
Yeah.
You could also do that. Okay. So that was it for the deep learning part. So there's another part which is about text processing with deep learning for J. So here it's about neural word embeddings, which were explained previously. So I will go over it a bit faster. So this is done using this node, which takes a table containing documents or words as inputs and outputs our word vector model. So neural word embeddings are, as we heard before, a transformation of text into a vector space. Now the dimensionality can be defined by a user, so because this this model actually uses another shallow neural network, so the user would define the number of output neurons of this network, so this would correspond to the dimensionality of the resulting word vectors. Then we can either transform single words or whole documents into a vector representation. And these vectors can actually be used in a lot of applications and have some very nice properties. So for example, to create input for deep networks like we've seen before. Then for these word vector models, we have two methods. The first method which is available is word2vector, which maps words to vectors. So similar words are grouped together and they are correlated with each another. And the second method is document2vector, so we can create a representation for a whole document. For this we need additional label information, so we need label documents, and this would correlate documents with labels. Here I have another example of a word vector model trained by Google, and here you can see some the vectors of some capitals and some countries projected by a PCA. And now, as we heard before, these vectors are able to model some relationships. So, for example, the relationship of capital country would have a similar distance for other words. So you could actually ask the model which word has a similar distance to the word Russia than the distance of between China and Beijing, and it would probably give you Moscow as an answer. So generally these work vector models have very interesting properties and can be very useful. So here next I'd like to show you the basic workflow, how you would use this in KNIME. So this is very, very simple. You just, again, use a file reader node, where you would read in some data. Then you would use the word vector learner node. There you can specify also some learning parameters, and then a vocabulary extractor, which gives you a table of either the document or the words and its corresponding vector. So here, example, we read in some data. Here we have the configuration panel where we can configure some learning parameters, and here in the layer size we would specify the dimensionality of our output vectors. And then after the vocabulary extractor will look like this. So here we would have a column showing the word, and here the corresponding word vector. So now how can we use this? I'd like to show an example of also sentiment classification, but not this is more a baseline approach, like compared to that we heard before. So this is about sentiment classification of IMDb reviews. So here the problem is we want to predict the sentiment of reviews from the Internet Movie Database. The general model would be to first create a numerical representation of your reviews, and then use any classifier to predict the sentiment. As data set, we have 2,000 reviews, which each has about 200 to 300 words each, and we have two classes, so we have positive and negative reviews. Then the baseline approach to create the vector representation would be, for example, to transform the documents into term space, which would look like this, so maybe to create bit vectors. So here in this representation, each column of your, or each index of your vector would correspond to a single word contained in your corpus, and then you would just flip it to 1 if that word is contained in your document. So you can create a representation of your document. But using this approach, your dimensionality can get very high depending on the size of your corpus, and it only uses word frequency information. Then compared to the word vector approach, we would just train a word vector model. And here the nice thing is that we actually can choose the dimensionality of our data, and because it's not only using these frequency information, but is able to correlate the words with one another, this generally leads to better document representations, which I will show you in the next example. So here you can see the overview workflow, how you would do the sentiment classification. Of course, again, read in your data. Then we transform the our strings into documents, which is a specific cell type, which are documents. Then here we would additionally assign a unique label to each of these documents, so we can perform so we can train a document to vector model. So because each document has a unique label, we get a vector. A vector for each of these documents. This is done here. So here use the word vector learner and the vocabulary extractor, and the result would look like this. So here we have a ID of our document and the corresponding vector. Next, we extract the class information from our documents and join them with our vectors, and which looks like this. So here you would have your column with your class information, and here the columns having the values of your vector representation. So now you can maybe visualize this to see how well your vectors are performing. So maybe we can use just a simple PCA, which would look like this. So this is the PCA of the vectors created by the work vector model. And you can see that it nicely is able to, that you here in this view you can easily separate between the classes. And if you compare this to the PCA of the term space vectors, we can see that they are more overlapping, and this gives a hint that these word vectors are actually better representations for our documents. Then the last step is to train a classifier. In this case, like the examples I showed you before, we do some pre-processing, then we shuffle it, partition it, then we use a simple multi-layer perceptron, train a network, use a predictor, and use a scorer. And here in this case, we achieve the accuracy of 96%, which is pretty nice. So these word vectors are very useful, for example, in this application to create nice nice representations for your documents. So now I'm at the end of my presentation. As a conclusion, it can be said, so with the deep learning for JNet integration, so this offers you to visually assemble a network. Then you are now able to use deep learning for regression and classification in KNIME. Then we can, of course, use the power of deep learning to create powerful predictors for complicated data sets. And we also can create meaningful text representations using these word vector models. So, thank you.
I think that we can play time for questions.
Okay, we use that image segmentation instead of image classification, which imposes some constraints on the data partitioning. We only want patches we don't want to divide patches from the same image to both training and evaluation. That should only distribute it into either training data set or to evaluation. Okay. I wonder if KNIME also supports image segmentation with nodes?
We have we have another image processing integration, so you can probably do it with that, but not with the deep learning stuff. So we currently have no node which performs the things on patches.
Maybe you were first in the market?
So I'm a very beginner, but
yeah.
What I like about TensorFlow is that it seems to be very easily integratable into my existing application.
Yeah.
That's just a shared object which I have to link to. But how can I use this thing in my existing application? Do I always need a full-blown Java environment or server-side computation power, or I mean, can I somehow generate code out of these graphs, which are quite tiny?
So you cannot do that. So the idea of this whole platform is that you create your workflows visually. So that is.
But is it merely meant for prototyping then, or is it really?
It's more for, so it's not for, it's an easier interface for all this machine learning stuff. So you don't have to be a hardcore programmer to use all these algorithms. So you can easily use the parts of all these or use these different machine learning algorithms which are implemented in those nodes, and you just need to, like the Legos, like put them together, and it works.
Okay, I like this very much, but
yeah.
But when you put this to production, how can you automate everything? Because in the end, nobody wants to click something if you have it in production.
Give a batch executor?
Maybe I can give this question to my colleague if he's here. Thomas, can you answer that?
Can you repeat the question, please? How to put that in production, right?
Yeah, maybe my question is stupid, I don't know. But
They presented here as basically the KNIME analytics platform, which is open source and also allows for integrating, like with text mining, network mining, image processing, also deep learning. It's just an example how to extend the platform. And on top of that, the KNIME.com AG, which is located here in the Technopark in Zurich, provides enterprise components. For example, for such deployments, to put that in production. So what you can do is basically take a whole workflow, put it, for example, in a server infrastructure, and then you have like web service interfaces, or you have a web portal, those kind of things which allows you to execute the workflow from the outside.
Okay, for example, by REST APIs or something
Exactly.
like that. Okay, but then it's always running in a separate process, finally. I can't integrate it easily by just linking to a library and feed it with my learned data or something like that.
There are different ways. I mean, we have different ways to export models. For example, we're also supporting the PML standard, right? PML, Predictive Modeling Markup Language. It's an XML standard for predictive models. There are different ways to represent those models. So it could be a way to actually export the model, or, as I said, you can always take the whole workflow. There are also ways to actually, if you have a model already, you can always convert it either, for example, SQL code, or you can also translate that into bytecode, for example, Java. And this, again, can be deployed into a database system for fast prediction or whatever you want to do.
Okay, thanks.
Welcome.
I was wondering why you are using deep learning for J and not other libraries like
Java.
TensorFlow.
Yeah, that's one reason, because it's Java, and our whole, we could use like TensorFlow, but this decision was made. So like last year, so actually this all started with my bachelor thesis, and I started using deep learning for J, and then I started doing the basic parts, and then this was integrated in the new software. So we could use or integrate or do another integration of TensorFlow, but that would be another project.
Okay. Maybe just a follow-up question. Are there any plans to include TensorFlow or TF-Learn, which is also a high-level representation, which you can have a kind of one-to-one correspondence to your nodes?
Not yet, no, but we have that on our roadmap.
Okay, great.
Maybe sometime in the future.
Yeah. And okay, no.
I was just going to ask, what are your experiences with using this in a Spark cluster?
Currently, you can't use that in a Spark cluster. That's also on the roadmap. I'm currently working on that. But all of that.
Why we can't learning for J is Spark?
Also, you mean outside of KNIME? So the raw deep learning for J and Spark?
Oh, okay.
So I didn't work with that yet.
Right.
Yeah.
I also have a bunch of questions actually. For example, I don't like this local binary response normalization for whatever reason.
Yeah.
But now I want to use maybe, let's say, batch normalization. Or is it easy to integrate it for myself, a new node? Or?
Yeah, you can write a node on your own. So we have an API for that. So.
And then the training takes quite a long time for AlexNet, you say 2 weeks or so.
Yeah, it's the original AlexNet.
Okay.
I meant the original.
Yeah. But are you planning to have something like a model zoo where you can share models and use pre-trained models?
Maybe not the model zoo hosted by us, but maybe created by the community if this is widely.
Because they have some like Huffing networks which are pre-trained.
Yeah, actually, the deep learning for J guys, they are currently working on an importer from Caffe.
Okay.
So in the future, there may be a node which can read pre-trained Caffe models.
Okay. More questions? I think then we have plenty of opportunities to ask more questions at the APRO, but maybe first thank the speaker again.